Welcome to Morton. You are the fifth talk in our 2025 online DOE Summit held by StatEase. We are turning 40 this year, so we are very excited to be hosting 8 wonderful speakers on different topics about design of experiments. Morton today is going to talk about experiments avoided through DOE, a topic that I am actually very excited to hear about because it's something that I often promote when talking about design of experiments, about how much time and money you really save by applying these statistical tools. So, Morton, if you would.
Thank you, and thanks for having me. So, hello everyone out there. My name is Morten. I am a product manager here at the Danish Technological Institute in Denmark, as the name might imply. I'd like to sort of introduce, just to tell you a little bit about who I am. I have a background as a chemist. I have a PhD in chemistry. And for the last 7 or so years, I've been working here at the Institute with technology development for companies. I'm one of the people who never heard about design of experiments before I entered industry, to my great regret, I would say. Today I sort of want to share a couple of examples of how design of experiments entered into my work life, and through some specific examples, and especially focusing on how DOE was used to sort of make sure that you do the adequate amount of work to solve problems. So we'll be jumping back and forth between a presentation and design expert as we go along. But let's jump into it. There you go. So I should say that even though we are called the Danish Technological Institute, it's important to know that we are not a university. My company is what's called a research and technology organization, which is sort of, you can think of it as the midway point between industry and academia, in that one of the things that we do, like many similar institutes in Europe, is that we take very low TRL technologies and push them into industry, make them work in the industrial world. We're spread out across a number of locations in Denmark. I am in the city called Aarhus, and sitting in this building at the moment. And we're about 1,000 people in total in my institute. So I wanted to start out sort of relating my journey into DOE, and also sort of motivate, for the sake of this video going on YouTube later, the whole idea of DOE. So as a chemist, when I was at university, we were often told that it was important to understand the processes that we were working on, or the reactions that we were investigating. And quite implicitly, when I say understand, it was usually meant that you need to draw graphs like these ones, where if you can tell using data that the quality of a reaction, or the yield of a reaction, changes with pH because this graph is steep, then you would say that pH affects your system. And if your graph is flat, you would say that a given factor does not affect your system. And at most Danish universities to this day, it's sort of implicitly assumed that since you want to end up with graphs that you can understand by just looking at them like this, it's also a good idea to collect data in a single factor fashion. But as I will now argue, this is not really a good idea, at least if you care about being efficient in your work. So I'm going to very briefly motivate DOE, even though I know most of the audience know about it. So one of the things that I have come to learn about DOE and talk about a lot when I teach DOE to companies is that when you vary things one at a time, not only do you miss good opportunities for better processes, but you quite often also learn wrong things. So in this example, you may imagine that a company has some process that could be affected by temperature and time. But this company has a lot of experienced employees, and they I'm pretty sure that the present settings that they use for their process, things can't get better. They have tried changing temperature and time several times, and things won't really be improved by that. And it may be that they are even able to show you data like this, where we have, let's just call it quality along the vertical axis, where changing temperature starting from the present setting actually decreases quality slightly. And changing the time starting from the present setting also doesn't do anything good for quality. They may be able to dig up these one factor at a time data sets to very conclusively demonstrate that nothing further can be done for this system. And when you don't use DOE, you often overlook the potential for really good results because you miss corners like this where the underlying landscape requires you to change two things at a time to reach a better process setting. I like to joke that if your process for baking cake in your kitchen right now is sitting at a process setting of 1 minute and 50 degrees, turning up the temperature to 200 or 300 degrees and putting in your cake for 1 minute is not going to bake it. And changing the staying at 50 degrees but changing the time to 20 minutes is also not going to bake your cake. So if you changed things one at a time, you would conclude that neither temperature nor time can bake a cake. And this is in many cases when companies begin using DOE, they discover a lot of process improvements very quickly because they begin varying multiple things at a time. So on the whole, especially when you are developing new products or processes from scratch, varying things one at a time is extremely inefficient. Even if there is a clear dependence of some factor that you change and you find a better setting, go to that and then change another factor and find an improvement further and go to that setting. Your final result or where you end up when you run out of budget is going to be different depending on which thing you varied first. And it doesn't really ensure that you get to the overall global best solution. And furthermore, real processes in industry don't just depend on two factors. They quite often depend on a handful or more factors. And it becomes very difficult to sort of keep the overview of where you've been and what your data is showing you if you collect data in this straight line fashion. And on the whole, this is what DOE was designed to overcome, where we don't necessarily really care about the individual data points, right, in DOE. We care about collecting data at a predefined set of points in a way that allows us to draw the underlying landscape. We care about finding or building this map so we can use the map to identify where we should set our process. And the focus of DOE is really on the map or the model in technical terms, right? So this data set of 9 data points was designed in a much more productive fashion than these 9 data points. Same number of work or same amount of work, but this is a much more productive result, right? So that's just to set the stage of why we're doing this. So today I sort of want to dive into 3 cases to illustrate how this approach to thinking about the landscape that you want to build will allow you to save work. I'll start out by talking about the project that got me into DOE in the first place. Then I'll give an example of an optimization study from the biotech world, and then end up with a coding problem and sort of illustrate what the cost can be if you don't use DOE in really large industrial R&D projects. And throughout all of these, we will jump back and forth between the presentation here and Design Expert to sort of give an example of how I designed, or how we could have designed in the last case, a DOE that would have been helpful. So let's start out with wood coatings and finding out the right ingredients to put in wood coatings. This is from a project with the Danish company Voka. They make wood care products for furniture and floors. And the goal, or the reason we worked with them in a project, was that they wanted to transition away from doing wood treatment that relied on organic solvents that are not very healthy and have a big environmental footprint, and instead do water-based products. But the central issue with that is that if you take floorboard of oak and brush it just with pure water, it becomes very rough because you have a bunch of fibers from wood that sort of lift up from the surface, causing you to, or which induces a need to sand down the coating that you just applied. So the project was centered around sort of handling this issue and minimizing the amount of raised grain that you would get in coatings that included wood. And when we started this project, this was before I had met DOE. So at the beginning of this project, we did a lot of experiments that were extremely wasteful. This is a couple of examples of them. So on the left, we had a formulation where we added some stuff to change the pH of the solution and to figure out if that affected raised grain. And then we did all of these experiments because, again, we didn't design these in any way. So we just figured maybe 2 experiments per pH value or something like that was adequate. And similarly with other ingredients, this was a filler we experimented with, where we, again, for no particularly good reason, carried out duplicates at certain values. And we did many variations of these kinds of one factor at a time studies. And the result of this was that after 1 year, I think we had run more than 200 different experiments, and we hadn't really learned much. We were sort of stuck. Then I happened upon a DOE book and the webinars from studies. Actually, this was how I got started, by watching a bunch of webinars from about the software. And then I went and did a first DOE. So what we were aiming to do here was to figure out the best combination of components in a formulation. It had, I think, a total of 7 or 8 components, but these were sort of the most important ones judged by the company. And for each of these components, there was a number of candidates from different suppliers that they figured could be useful. And you can combine these, as I've written here, in 320 different ways. And then our goal was to sort of figure out a combination that would allow us to pick one from each category. Then they would make that formulation, apply it to some floorboards, and measure a bunch of things that had to be within a certain product quality range to get a useful product. So I will jump over into Design Expert to sort of show you how that looked. So let's go in here to Design Expert. So this is actually the full data of from this design. And just to show you what that design process looked like, I'm just going to redo the design while you're watching here. So as I showed you, that we have a different number of levels of potential components, and this to sort of figure out which one to use. At the time, we just did a main effects model, and we figured that 30 would be a useful number of runs to do. And I won't go into sort of the power calculations, because at the time I actually didn't understand power calculations, and I didn't fully grasp the design process. But I think the reason why I want to admit that is that this was still a useful experiment, because it was much better than testing all 320 at the time. So here's a picture of the 30 subsequent samples that were generated in this main effects design. 30 was more than enough to fit a main effects model in this system. And we discussed interactions at the time, and actually we had good chemical reasons not to expect them. So there was no reason to include that in the design process, even though we could have done so. And one of the important factors is color change. So, and I want to sort of highlight one replicate that happened to have a lot of color change, even though this was not a desirable feature. So there was a couple of replicates in this design. Yeah, and based on these 30 samples, we were actually able to identify a combination that was not among the 30 tested, that where the prediction on each of the quality features suggested a new combination that might pass the overall requirements for an acceptable product. And here I'm showing you sort of the comparison of this combination where this water-based primer has been added to oak. And one of the design requirements was that this primer should not change the look of natural wood. So this is just a visual comparison of that. And this allowed us to, in this case, find a combination that passed validation, and Walker got a new product out of that. So from we started out designing this first main effects design until we had the validated final product, that took 3 months. Because the number of experiments, they did all of these, prepared these 30 formulations in parallel, and we did a lot of testing in a very sort of focused manner. But that was all it took to find something that was good enough. And then we had 2 candidates, and we did 2 rounds of each for validation. And contrast this with the previous or initial year of project work, where we did more than 200 different runs and ended up in a situation where we had made essentially no progress towards the goal. So I think this was really what hooked me on the idea of DOE, that not only had we spent 1/4 of the time and roughly 15% of the work of the first part of the project, we actually got all the way to the final project goal within those 3 months. All right. So that was where I sort of started out. This was just a screening design, and I think that's pretty common for most people, that you start out with something that's relatively simple in a combinatorial fashion. The second case I want to talk about is from the biotech world. This was a collaboration with a startup that was working with a type of stem cell treatment. And they were sort of at a stage where they needed to improve their cell yields and the amount of expression of certain key proteins involved in this treatment in order to be able to proceed to clinical trials. They simply needed enough of these stem cells, and they had to be in a certain state for them to even progress into clinical trials. And what we had the option of varying here, what they were interested in figuring out, is that there were up to 4 things that they could reasonably control in sort of the growth medium for these cells. And a really important limitation was that they had enough of the starting stem cells to do a total of 100 runs. And with the important practical consideration that these growth experiments for each run, it takes 2 months for the cells to go through their full growth and differentiation before harvest. So it was really quite important to figure out what is the right balance of the amount of runs that are needed to put into optimizing this process, preferably without using all of the materials, so there would be space for several rounds. But also, we can't do too many iterations because they were also on a clock in terms of when they needed to be ready for clinical trials. Now, for at this stage, building an optimization model, it's important to sort of realize what we are aiming to achieve when we do this kind of work, because it's different from picking the right combination of components, as I showed you in the first example. So the important part here is that they wanted to optimize the growth process, which means that they want to find, or essentially predict, some setting along each factor where they should, place their default process. And it's very easy to draw that in principle, that we want to figure out where, what this line is of how the quality or the stem cell yield depends on the things we can control, find the highest point and just put the process there. But in reality, what we get out of our experiment is not this line. We get some interval where the line could foreseeably be located. So we get some interval where we predict that the underlying system behavior is located. We can even go so far as to look at tolerance intervals where new data points will end up. But it's important, if we want to make a choice of putting the process here, that our predictions look like what I show you here, that the uncertainty of our predictions are narrow enough to be useful. Because getting a model out where the predictions look like this is maybe not something you should trust or make decisions on. So how do we know what we're going to get in advance before we actually go out and run the experiment? Because if this is what a design is going to provide us, then we need to do more runs to bring the uncertainty down to something that we can use like this. Okay, so for this particular optimization design, I sort of want to showcase the design process for figuring out a good amount of experiments to run by use of the fraction of design space graphs. And I'm just going to do it for one of the responses, and also just highlight that in most cases when you have more than one response, the limiting factor for your design is just going to be the response that has the highest relative amount of noise. So you can say your worst response measurement is going to be what dictates the amount of work you have to do. So in this case, we're going to look at a response that's basically a proxy for whether the cells are healthy or not in a percentage out of the percentage of all of the cells. And this company that we were assisting in this case, they had a bunch of historical data where they had done a bunch of replications of this type of measurement. So we had a rough idea of what the noise is in this measurement. And I'm also just showing you sort of the starting values, because this will be sort of important to demonstrate what they got out of it. But let's jump back into Design Expert and look at this particular case. So I'm just going to close the first one down here and find case 2 here. So to start out, in this case, we had 4 factors, which was 3 different things that could be added to the cell growth medium. And just for reasons of confidentiality, I've just coded it as percentages of their starting conditions. So they were for each of them, they could either decrease the amount of compound A they put in or increase it by a lot. And similarly for B and C, while factor D is sort of the overall dosage that they of these compounds that they put into the growth medium. And in this case, they cared about the percentage yield. So how many cells per cell do we get out, because they want to multiply them, and how many of the cells that they get out are healthy. So in this case, I've created a design, and I guess we can actually just go through that because we have time enough. So in this case, we are looking at building a quadratic model, because they want to find an optimum for each of them. They're all continuous factors. So we cared about a quadratic model, and there was some initial, in principle, you don't need very many runs to build a quadratic model in 4 factors, but after a bit of back and forth, we need to sort of get to a level of runs that's somewhere around 50 or maybe more to get adequate models. So this is sort of the starting point. And so I will just finish this up so we get the design, and then go into the design evaluation and click forward to the fraction of design space. Now, this fraction of design space is one of the concepts that I have struggled the most with learning when it comes to the DOE world. So if you're new to using this approach to sizing your optimization designs, I very highly recommend that you go and take a look at the webinars that treat this, sort of how to approach this. For those of you that know, so the noise of this particular measurement of the cell health is about, the standard deviation is about 4.5%. And in this case, what I did to sort of figure out various designs was to sort of play around with the precision that would give us a coverage of 95% of the space. So basically tune this value up and down until we get an FDS of 95 and say, okay, this is sort of the level of precision we can expect for this system. Because then we can repeat that exercise for a different number of runs and compare them and figure out where the quality of the data is or the quality of the design. So, but on the whole, you can basically say that the fraction of design space sort of summarizes where in your space you can expect your model error to be below some value. So obviously, when we do a design experiment, the errors are going to be largest in the corners because there we're not surrounded by data. And this, the use of fraction of design space basically tells us where this precision is going to be, or the error is going to be below some threshold that we choose. Right. So I won't harp about that. It's a very useful tool, so I will highly recommend that you watch the webinars to sort of learn to use that. So, but basically what we then, once you learn to use fraction of design space as a sort of metric for how good is this optimization design going to be, it makes sense to generate a bunch of different designs so that you can compare them and you make an informed choice. So the design that we just looked at is number 2 here, where we included all 4 of the available factors and used a total of 50 runs distributed in a specific way. And if we go with that design, we can expect that the final model that we end up with is going to have a prediction interval that is plus or minus 4.7% or narrower in 95% of the total experimental space. Now, you can compare this to, for instance, using a lot of the budget, so 80 runs. That will give you, narrower prediction intervals. But in terms of, the amount of information that you need to make a decision on whether to change the process, this is not a particularly, a greatly more precise model than this one. We also compared the scenario of maybe we don't have to include all 4 factors. So the dosage factor, when this company came to us, they weren't sure whether they should include it in the optimization or not. So we also did a design where we only used 3 factors and a total of 30 runs, and to really save work. And that's going to result in a model for cell healthiness that is about as precise as if we include all 4 factors and use 40 runs. So compared to sort of the total amount of work, this doesn't really save very much. So they could essentially include the 4th factor at no additional cost. They might as well do it since they're making a designed experiment anyway. So in the end, we had a long discussion about the advantages and disadvantages of these potential designs. And they ended up going with the design number 2 here, spending 50 runs, which was half their cell budget, and then did a validation run afterwards. So they got this worksheet for this design, and then went away for a couple of months to run all these experiments over the course of the summer. And the model that they ended up with allowed them to find a different set of settings that were able to boost the percentage yield of cells by almost 4.5 times, and also increase the healthiness of the cells compared to where they started out with. And the settings that turned out to be able to provide this included changing all of the factors. So it's one of the things where if they had done their experimentation just varying 1 factor at a time, they would actually not have found these settings that allowed them to obtain this improvement in their process. So In this case, there was a relatively clear task: is sort of find the best possible settings for the various things we are measuring on our cell process. We only needed to use half of the available cell budget, and were still able to identify very different settings that improved their cell health and increased the yield of this process 4.5 times. As part of the design process, we discovered that it would not really cost them anything extra to include all 4 factors. And this meant that after these 2 months of this optimization design, they could then do a single round of validation, which was still in time for their phase 1 clinical trial, and get to a state where they could meet their next funding gate, which is important when you're a startup. All right, so these were a couple of examples of saving work using DOE designs that I have built myself. And now I want to sort of use a little bit of a funny horror story about the consequences of not knowing about DOE in a large research environment. So some years ago, I was approached by a very large European paint manufacturer who had a very big Excel sheet where they had designed a bunch of experiments by hand. And it was conceptually very similar to the first case that I showed you. They were experimenting with different possible choices of ingredients. So here A is one type of ingredient for paint, and B is a second type, and so on. And even though there are percentages here, the relative amounts are actually fixed. And for each of these samples that they had tested, they had carried out a bunch of measurements, and it was all quite confusing and not very nicely structured because they hadn't used the DOE software. So just to provide you a bit of an overview, this is actually exactly like the first case in that there were 5 different factors that were varied. It was, and they were treated as categories where you had a number of options within each. And but they were all at fixed ratios. So the total amount of polymer was always the same. The total amount of mineral was always the same, and so on. And this all added up to 100%. And you can combine this in 1,350 possible ways. But they had only tested 180 different combinations within this space. But they had not chosen those 180 combinations with DOE. But 180 of them in duplicate, which resulted in 360 panels that were coated with this paint, and then subjected to a 6-week accelerated aging test in a big expensive machine. So the duplication part was, again, for no particularly good reason. They were aware that there was noise in their measurements, but they figured duplicating their experiments would probably maybe handle that. So this was quite an expensive study and a very large amount of work. So I think the total labor and ingredient cost for a single panel is on the order of $1,000. So you can sort of figure out how expensive this was to do. But let's look at the data set that they had actually collected and what we can learn from it, just as it is. So I'll close this design here and open the full data set here. So this is the full worksheet of 360 data, or 340, sorry, data points. What can we learn for this? What model can we even build? So maybe I will just start by showing you sort of how these data are distributed if we just plot it as a function of a couple of these factors, because that will allow us to see that things are maybe not looking so great. So for one, here you can see that it's definitely not an even spread across the filler here. It has not been tested at the same level at all. And maybe let's change this one to here. So it's for the top up. The different options for top up have only been tested with one polymer, not with all of them. So this is a completely unbalanced design and a bit of an omen of things to come. So we'll just look at one of the three things that they measured for each of the panels, and I guess color change because that's easy enough to understand. And already in this window, if we look on the right on the possible models that we can build, things are not looking great. And having looked at the distribution of data points, we understand why. In this case, I mean, there is enough to estimate the main effects, obviously, because each level of each of the components have been tested, included in the data. But already the two-factor interactions, we run into trouble, and because we have aliasing, and we can't really go higher than that. And this is also quite apparent in the ANOVA, where there is an extremely significant lack of fit, and there are very many things that are wrong here. So it would be extremely dangerous to begin to make decisions about, the product makeup or combination of these components based on this model. All they could hope for is essentially that there are no interactions at all, and then just look at main effects for this system. But as a chemist, I can tell you that this is gonna go wrong very quickly. So the interesting question is, of course, what could they have done differently, and what could they have achieved with the same budget or smaller budget? So I think I had that prepared here. So I will sort of go through the design process for this system, and just assume that this amount of levels for each of the factors is for some reason a good idea. So let's stick with this amount of combinations. And in our design model here, just build a two-factor interaction model. That's maybe reasonable for this kind of design. And that is, with this number of levels, it's going to require a pretty substantial amount of work still, 130 runs at least. But if we sprinkle in a couple of additional model points and like a fit points, and use the values for the noise and the signal that they wanted to detect, we can actually look at, so these are just default values, but we could have looked at this design and see that the power was actually enough for getting a two-factor interaction model, even though this only required 180 runs to carry out. Another option, of course, would be to, if you had known DOE at this stage, is at the design phase to maybe question whether running 6 levels of the polymer is actually necessary. Maybe you could foreseeably identify maybe 4 of them that you suspect are the most obvious candidates, and reduce the space a little bit. So I've prepared another option here where we imagine that it was maybe possible to just remove 2 levels from this factor and then leave everything else as it was before, and still aim at the goal of building a 2-factor interaction model. That will allow us to drop the number of experiments further. And again, we are, with programs like Design Expert, we can look at the power both of the for the main effects model, but we can also look at the power for the 2-factor interaction terms, to see that there's sort of this design is like right on the border of having good power for the interaction terms. which is not bad for an experiment that, in this case, would only involve 130 runs. Okay, so to sort of summarize this stage, what could this company have won if they had used DOE? Well, being a little bit more critical with sort of the design space and then trimming the amount of levels in the first factor, the polymer, they might have been able to get down to as little as 130 runs to build, and that would still allow them to build a full two-factor interaction model. But what they had done instead was to use 360 or 340, maybe that was the right number, but still substantially more runs, and still only come out with a main effects model at best. And this amount of samples to test was really expensive. It requires several rounds of these very long-term aging tests where you subject panels painted with each combination to simulated rain and sunshine and heat and so on. And they could have cut that at least in half and saved quite a substantial amount of money. And at the stage where they were with the data that they had available to them, it was really not enough to make a decisive conclusion on which combination of ingredients that they should use for the paint that they were investigating. But they could have achieved that with just 130 runs had they spent the time and effort to design this with DOE. Okay, so this was three quite different examples of how DOE can save you work, starting from a relatively small experiment with 30 runs, where we got a good result despite not being able to, at this stage where this project happened, we weren't proficient yet in sort of diagnosing the exact right amount of runs that we built, but just having a design process helped immensely here. Then we looked at this biotech example where we had 4 continuous factors, and they were looking to optimize the yield of a process. And they were able to do that plenty within their budget and strike the right balance between the amount of work, the risk, and the need to explore the space and achieve better process outcomes. And finally, the last example here, we saw how when you have large R&D projects with a lot of stuff you want to investigate, DOE can really save you a lot of experiments. And if your experiments are expensive, and most experiments typically are, if nothing else, in time, it could have saved this company almost $150,000, and they would have gotten a better result in terms of knowledge for the decisions that they were looking to make. So with that, I want to say thank you for your attention out there. If you have any questions about these particular cases or how we approach DOE in general, you are quite welcome to contact me on this email here. And I think with that, I'll stop sharing my screen and sort of jump back to the camera view here and ask whether there are any questions from the audience.
We do already have one question from an Italian food technologist, and they would like to ask why such a powerful instrument remains so underutilized in R&D within the food industry. We would also like to know that.
It's a question that has many answers, and I think there are many different reasons for it. I think it starts in the educational system. Like, as I said, I'm a chemist by training. I did a PhD in the experimental chemistry sciences, and at no point during my 8+ years in university did I even hear of the concept design of experiments. So I consider that, at least in the Danish educational system, a massive failure in terms of how we structure our education. But then the obvious follow-up question is, well, why don't we just put it into the educational system? And I think that has different answers in different countries, and I know that there are some countries where people are good at putting this or have this as part of their educational system, particularly in engineering disciplines. Um, but what I faced here in Denmark, and I'll just speak for my own country here, is that the thinking goes a little bit like this. So if I go to a professor now and tell them about design of experiments and as a concept and what it can do also for knowledge work, they will have this gut reaction of if something as good as this existed, I would have heard about it by now. Since I haven't heard about it, it can't be true. And overcoming that feeling is extremely difficult. Um, so I don't know how to fix it. But I mean, and this is why I spend most of my work teaching design of experiments to companies now. It's not very difficult to pick up. It doesn't take that long to implement in a company. You can do a lot of self-teaching using webinars such as the ones on Study's YouTube channel, and I highly recommend that. Yeah, but I don't have a universal good answer for it.
And I will say the last math class I took was in 2008, and I was able to run a DOE in 2016
Yeah,
with minimal
the,
help from
the
Patty's
barrier
consulting.
is not the stats. Like most people think that it's because statistics are difficult, and it's really not for DOE. Like in terms of stuff that you learn as a scientist, whether you have a bachelor, master, or PhD, doesn't matter. You learn a bunch more difficult stuff than the math that it takes to run DOE. So that's not really the barrier. I think a much more practical barrier in many companies is just understanding variation and measurement system error is is undertaught. But if you begin looking at how good are our measurement systems, you don't typically become very popular. Because it's often a very unwelcome truth that you discover once you begin running a gauge R&R study on processes then or measurement methods that may have been in this company for 10 or 20 or 30 years, and you are able to quite conclusively prove that most of that measurement signal is just noise. That doesn't win you a lot of friends initially. So it also requires an organization that for better or worse, is able to be humble enough to admit that they can do stuff better, and that requires a certain company culture for that really to be realistic. So those are a couple of observations about the practical barriers of that.
Next question. Do you have any experience with p hacking?
Well, I can understand that question can be interpreted in several ways, right? It's do I have any recommendations and experience in how to do it, or I'm not sure
Well,
what it
the
means.
follow-up is, can you touch on ways to avoid p hacking?
Yeah, okay. So yeah, I guess it becomes when you are at the design stage. So like using DOE is a pretty good way of preempting p hacking, and mainly because when you follow sort of the recommended process for doing DOE, that you can also go through the tutorials of Design Expert, and you'll sort of see the recommended process. It forces you to put in writing what is the effect size you care about finding. Not whether that effect is significant or not, but I think what's much more important, both when it comes to academia and industry, is saying what effect do I care to find, and then being prepared to do follow-up validation of whatever your finding is from a study. So I think p hacking is especially a problem when you expect the study and the ANOVA to be the one thing you ever do. If you make a wrong conclusion during the ANOVA, and maybe your data just turned out magically so that one factor appears significant, you should always validate it in a real workflow. And so no matter what the p-value is, it doesn't protect you from being wrong or some external factor influencing your experiment, right? So so I think requiring validation or insisting on validation always, if nothing else, is going to protect you from making the wrong conclusion from just a single ANOVA. Yeah, I think that's maybe the main recommendation from my part.
All right. Next question. Do you think DOE would be useful when we have variables with high variability? For example, as part of my recipe, I have potatoes from different parts of the world, peanuts, variability in the process as well, etc., etc. Or what would be some considerations that I should pay attention to?
Yeah. So this is a very common problem, and it's going to be a bigger problem in the future when we make more and more things bio-based, because suddenly when we make plastics, we will also face raw material variation. So I think the first thing I will comment is that in cases like this, where your input is a plant or something from a biological process, you need to be extremely careful that your conclusions are not just caused by raw material variation. So in your example with potatoes changing year from year or from different locations, you really need to consider using things like blocking to sort of handle or account for system drift over time. So I mean, with DOE, we sort of semi-protect against system drift by randomization. But if the drift is on a time scale that is longer than your individual designed experiments, you really need to be careful. Some recommendations would also be to have some standard either process or recipe that you periodically redo. So if you have a food recipe that contains particular potatoes and some other vegetable, I would periodically revisit each time there's a new batch, do the standard recipe, and measure the the quality metrics. And you don't have to do this super frequently to discover if there is large scale drift over time. And if there is large scale drift over time and you can foresee it, you need to make sure that the conclusions that you draw about various effects, that you sort of put them into the context of how big are the effect sizes compared to the scale of the system drift. So as an example, let's say you are extracting starch from potatoes, right? And you discover some factor, let's say the stirring speed in your pot changes the yield of starch by 1% by going from the low to the high setting. But over time, you have data showing that just the starch content at a fixed process varies by 10% up and down, right? So in that case, you really need to sort of keep in mind the scale of these effect sizes compared to each other, and be aware that in the future you might just get a new potato batch in and suddenly the yield is much lower, and that could quite foreseeably be because this batch of potatoes is different than the former one, not necessarily that there's suddenly anything wrong with the process. Yeah, but handling raw material variation is difficult. The best thing you can do is if you can find features of your raw material that you can monitor and use to build a descriptive or predictive model of why you see changes in your output as the raw material changes. It's difficult to do because you can't induce the changes, deliberately. But if you at least, instead of just recording that this was potatoes from South America, this was potatoes from Europe, this was potatoes from somewhere else, maybe measuring more things about the raw material will allow you to build a predictive model that can correct for the seasonal or the year-to-year variation. so that you can tune your process in an optimal way anyway. But it's a very complicated topic to sort of get into, and there's a lot of stuff to learn in terms of how to handle that.
What you're saying about finding ways to quantify the different things instead of just having these categorical factors echoes what Andrew was saying on Monday with how he was doing his coffee experiment. So if you missed that talk, it will be up on YouTube hopefully today. It's that particular video is proving a little more difficult to get online. Um, but yeah, definitely check that out as well. We are at time, so if you still have questions for Morten, please go ahead and send them to StatEase or Morten, did you provide contact information?
Yeah, on the last slide, so
Okay,
it'll be there as well.
yeah. Or you can send them directly to Morten. So thank
You
you,
can find me
everyone.
on LinkedIn as well if you just find my name. It's relatively unique enough that you can just contact me there as well.
And he's very popular on LinkedIn.
Thank you.
So thank you everyone for attending. We still have 2 more days of talks for the 2025 Online DOE Summit, and we look forward to seeing you at all of those. Any final thoughts, Morten?
Um, Again, thanks for having me, and I also look forward to the coming days of talks.